All right, buckle up, everyone, because today we're diving headfirst into the mind-blowing world of electromagnetic waves.
You know, those invisible forces that are literally everywhere doing all sorts of crazy things.
Yeah, like think about it. They're the reason your phone works, why you can see the colors of the sunset.
And even how doctors can see inside your body with x-rays.
It's wild. And we're going to unpack all of that and more using Chapter 8 from our trusty physics textbook as our guide.
You might think physics textbooks are dry, but trust me, this stuff is anything but boring.
Oh yeah, get ready to have your mind blown. We're going to explore how a changing electric field can actually create a magnetic field.
And get this, we're going to figure out how the speed of light is determined by the very fabric of space itself.
So our mission today is to demystify these waves, understand how they work, and see why they matter so much to, well, pretty much everything.
And I think we should start by giving a shout out to the brilliant mind who first cracked this code, James Clerk Maxwell.
Maxwell. Wasn't he like a super famous physicist or something?
He was. He took what we knew about electricity and magnetism and totally revolutionized our understanding of it.
Yeah, I remember something about Maxwell's equations from school, but honestly, it's all kind of a blur now.
Well, don't worry, we're going to break it down. So Maxwell was working with this thing called Ampere's law.
Ampere, like the unit of electric current.
Exactly. And Ampere's law describes how electric currents create magnetic fields. Think about it like this. When electricity flows through a wire, it actually makes a compass needle move.
Oh yeah, I've seen that before. So that's because of the magnetic field created by the electric current. Cool.
Right. But here's where things get interesting. Maxwell decided to apply Ampere's law to something called a capacitor.
A capacitor, is that like one of those little components you find in electronics?
That's exactly what it is. They store electrical energy.
Okay, so how does a capacitor fit in with this whole magnetic field thing?
Well, the thing about capacitors is that when they're charging up, there's this gap between the plates where no electrons are actually flowing.
Wait, so there's a break in the circuit, but the capacitor is still getting charged.
Right. That's the key point. So if there's no electron flow between the plates, Ampere's law would say there shouldn't be a magnetic field there.
Right.
But Maxwell suspected something else was going on. He realized that even though there's no flow of electrons, the electric field between those capacitor plates is changing as it charges up.
So he's saying that a changing electric field can actually create a magnetic field. Didn't we learn that Faraday already figured out a changing magnetic field can create an electric field?
You're exactly right. So now we have this beautiful symmetry, right? They can generate each other.
Whoa, so it's like this never-ending dance between electric and magnetic fields, each one giving rise to the other.
That's a great way to put it. And this back and forth is what sets the stage for electromagnetic waves.
Okay, I'm starting to see how these fields are linked, but how do they actually break free and become, a wave that can travel through space?
The secret ingredient is acceleration.
Acceleration, like speeding up or slowing down.
Exactly. Anytime an electric charge accelerates, it creates this disturbance in both the electric and magnetic fields around it.
So it's like shaking a charged particle back and forth.
That's the idea. And these disturbances ripple outward at the speed of light.
So every time an electric charge changes its motion, it sends out these ripples of energy.
Yep. Think about it. When you turn on a light switch, you're causing electrons to accelerate in the wires, and those accelerating electrons create electromagnetic waves.
Whoa, so I'm creating these waves just by flipping a switch.
You got it. And you know what's even cooler? One type of these electromagnetic waves is light itself.
Hold on, are you telling me that the light from the sun, the colors we see, it's all just electromagnetic waves?
Exactly. Light is just one small part of the whole electromagnetic spectrum.
Okay, now my mind is officially blown.
But let's not get ahead of ourselves. Let's zoom in on these waves a little more.
Yeah, okay. So what do these waves actually look like?
Picture this. You've got the electric field and the magnetic field, right? And they're both oscillating, like vibrating perpendicular to each other.
Okay, so it's not like a sound wave where the air is compressed and expanded in the same direction it travels. It's more like shaking a rope up and down. The wave travels along the rope, but the actual movement is perpendicular to that.
You got it. That's a perfect analogy.
And this whole thing is zipping along at the speed of light.
Which is, by the way, a ridiculously fast speed. We're talking 186,000 miles per second.
Yeah, that's like going around the entire Earth 7.5 times in a single second.
Crazy, right? But here's what's even more mind-blowing. That speed isn't random. It's actually determined by the universe itself.
What do you mean by that?
It all comes down to two fundamental properties of the universe: permeability and permittivity of free space.
permeability,
But
and
what was the other one? Permittivity. Basically, permeability is how easily magnetic forces can act through space, and permittivity is how easily electric forces can act through it.
so these are like properties of empty space itself.
Yep. And it turns out that those two properties are what determine how fast electromagnetic waves can travel.
So it's like the speed limit for light is built into the very fabric of the universe. Whoa.
Isn't that wild? And here's another thing. All electromagnetic waves, no matter their frequency or wavelength, travel at the same speed in a vacuum.
So whether we're talking about radio waves, microwaves, X-rays, they're all zipping through space at the speed of light.
That's right. But if they're all traveling at the same speed, what makes them different?
Yeah, good point. Like how come X-rays can see through my bones, but radio waves can't?
The answer lies in their frequency. That's how many times those electric and magnetic fields oscillate per second.
Okay, so frequency, it's like
Yeah.
different notes on a musical scale. You can play them all at the same volume, but what makes them sound different is their pitch, which is determined by the frequency of the sound wave.
Exactly. Higher frequency, higher pitch. And just like musical notes, electromagnetic waves are organized on a spectrum based on their frequency.
Ah, so that's where we get the electromagnetic spectrum. It's like a cosmic keyboard.
From incredibly low frequency radio waves with wavelengths longer than a football field.
To super high frequency gamma rays with wavelengths smaller than an atom. It's mind-boggling.
It is. And all of these waves, from radio waves carrying our favorite songs to the gamma rays produced in nuclear reactions, they're all just different frequencies of electromagnetic radiation traveling at the speed of light.
It's like the universe is playing this amazing symphony with all these different frequencies blending together.
A cosmic symphony. I love that. But even though they're all part of the same family, each type of wave interacts with matter in different ways.
Right, which is why they have such different effects and applications.
And speaking of applications, let's take a quick tour of the electromagnetic spectrum and see what each type of wave is up to.
Awesome. Lead the way.
Let's start with something we're all familiar with, visible light. It's just a tiny sliver of the entire spectrum, right between infrared and ultraviolet radiation.
Oh yeah, visible light. That's what we see with our eyes, right?
You got it. And the colors we see, from red to violet, they're all just different frequencies of light.
So red light has a lower frequency than violet light.
Exactly. And red light also has a longer wavelength. Remember, longer wavelength means lower frequency.
Got it. So what's beyond violet light on the spectrum?
That would be ultraviolet radiation, or UV. We can't see UV light, but we can definitely feel its effects.
Oh yeah, like when we get sunburned.
Exactly. UV radiation has enough energy to cause chemical reactions in our skin, leading to that lovely sunburn.
Ouch. And what about those black lights that make things glow in the dark? Are those UV too?
You bet. Some materials can absorb UV radiation and then re-emit it as visible light. That's called fluorescence.
So it's like the UV light gives those materials an energy boost, and they release that energy as light we can see. That's so cool.
It is pretty neat. And as we move further up the spectrum, the energy keeps increasing. We get to X-rays and gamma rays.
Which are known for their ability to penetrate through things. Like X-rays can see through my body.
That's because they have enough energy to pass through tissues that are opaque to visible light.
Yeah, they go right through my skin and muscles, but get absorbed by denser materials like bone.
Exactly. And gamma rays, with their even higher energy, can actually break apart atoms.
So they're used in cancer treatment to target and destroy those harmful cells.
You got it. But now, let's go back down the spectrum a bit. What about infrared radiation?
Isn't that what we feel as heat?
You got it. It causes molecules to vibrate, which increases their thermal energy.
That's why those heat lamps at restaurants feel so warm. They're emitting infrared radiation.
Exactly. And then below infrared, we have microwaves.
Microwaves. Used for more than just heating up leftovers, right?
You're right. They're also used in communication and radar systems.
But in a microwave oven, the frequency of the waves is chosen to match the resonant frequency of water molecules, right?
Exactly. So when microwaves hit your food, they cause the water molecules to vibrate like crazy, generating heat and cooking it from the inside out.
It's like a targeted attack on the water molecules.
That's a great way to put it. And finally, at the very bottom of the spectrum, we have radio waves.
Radio waves, the masters of communication.
They have the longest wavelengths and lowest frequencies, which makes them perfect for transmitting information over long distances.
Yeah, think about it. Radio broadcasts, TV signals, Wi-Fi, cell phones. It's all powered by radio waves.
But our modern world would be unrecognizable without them.
It's amazing to think that all these different types of radiation, from the radio waves in my headphones to the gamma rays blasting through space, are fundamentally the same thing: electromagnetic waves traveling at the speed of light.
And it all started with Maxwell's brilliant insights.
Yeah, we've come a long way from those capacitor experiments. But I'm still curious about how these waves actually interact with the world around us. We know they're made of electric and magnetic fields, but how do those fields affect the stuff they encounter? Like, how do they make things heat up or glow or will do all the amazing things they do?
That's a great question, and it's what we're going to explore next. Get ready to delve into the nitty-gritty of these electromagnetic interactions.
All right, I'm ready to dive deeper. Hit me with it.
It all boils down to the fact that, well, everything around us, all matter, is made up of these tiny charged particles, electrons and protons.
Right, those little guys?
Yeah, and when an electromagnetic wave comes along, its electric and magnetic fields can really mess with these particles, like shake them up.
So it's like the wave is throwing a party and all the electrons and protons are invited to dance.
Haha, that's one way to put it. And depending on the frequency of the wave and the type of atom or molecule it encounters, well, this dance can have all sorts of different outcomes.
Okay, that makes sense. But what are some real-world examples? Like, how does this actually play out?
All right, let's start with something we experience all the time: heat.
Okay, sheet.
So when infrared radiation hits a material, it basically makes those molecules vibrate faster, and, that increases their thermal energy.
So that's why we feel the warmth of the sun or a fire. Those molecules are just dancing to the infrared beat.
Haha, exactly. Now, think about visible light.
Yeah, okay.
We know different materials can absorb, reflect, or transmit light. That's why we see different colors, right?
Right, right. Like, a red apple absorbs most colors but reflects red light back to our eyes.
Exactly. And some materials, like glass, are transparent, so they let visible light pass right through. But others, like a brick wall, are opaque.
Because they either absorb or reflect all the light, so we can't see through them. It's crazy how different materials interact with light in such different ways.
It is. Now let's pump up the energy a bit and think about ultraviolet radiation, UV.
UV radiation. Yeah, that's the stuff that gives the sunburns, right?
Yeah, that's the one. It has a higher frequency than visible light, so it carries more energy.
Oh, I see. So more energy means it can have a bigger impact when it interacts with matter.
Right. And that's why it can damage our skin cells. But some materials react to UV radiation in a different way. Remember those black lights we talked about earlier?
Yeah, the ones that make things glow.
Those. Some materials can absorb UV radiation and then re-emit it as visible light. It's called fluorescence.
It's like the UV light gives those materials an energy boost, and they release that energy as light we can see.
You got it. It's pretty cool, huh? Now let's go even higher up the energy scale. What about X-rays and gamma rays?
X-rays and gamma rays.
Hmm?
Those are the heavy hitters, right?
You bet. They have incredibly high frequencies and energy, so much so that they can pass through many materials that are opaque to visible light.
Right. That's how doctors can use X-rays to see inside our bodies.
Exactly. They pass through soft tissue but are absorbed by denser materials like bones, creating an image. And gamma rays, with their even higher energy, can actually break apart atoms.
Wow, that's intense. So they can be used to, like, target and destroy cancer cells.
That's right. It's amazing how the energy of the wave determines how it interacts with matter.
It is. It's like gentle vibrations with infrared can make things warm, but those high-energy gamma rays can actually break things apart.
That's a great way to think about it. But there's another layer to this whole wave thing that we need to talk about. Earlier, you mentioned that electromagnetic waves can act like particles.
Oh, yeah, that whole wave-particle duality thing, it's been bugging me.
I know, it's a weird one, right?
It is. How can something be a wave and a particle at the same time? My brain can't handle that.
I hear you. It's one of the most mind-bending concepts in physics. For centuries, scientists debated whether light was a wave or a stream of particles. And the answer turned out to be both.
Both. Seriously.
Seriously. Experiments have shown that light can act like a wave in some situations and like a particle in others. It depends on how we observe it.
Okay, I need an example. Like something I can picture to help wrap my head around this.
All right, let's talk about the photoelectric effect.
Photoelectric effect. Rings a bell, but go on.
Basically, when you shine light on certain metals, it can actually knock electrons loose, creating an electric current.
Okay, so the light is giving those electrons enough energy to break free from the metal.
Right. But this only makes sense if we think of light as a stream of particles called photons, each carrying a specific amount of energy.
So the photons are like tiny bullets of light energy that can slam into electrons and knock them free.
You got it. That's the particle side of things.
Okay, so that's the particle side, but how does the wave idea fit into this?
Well, light also exhibits wave-like properties like interference and diffraction. Remember those?
Vaguely? Maybe. Remind me what those are again.
All right, so interference is when two or more waves overlap, creating areas where they either reinforce each other or cancel each other out.
It's like when two sets of ripples in a pond collide, right?
Yeah.
Some areas get bigger waves, and some areas become flat.
Exactly. Now, diffraction is the bending of waves as they pass through narrow openings or around obstacles.
Okay, I think I remember that from physics class. So we're saying that light can act like a wave when it's spreading out and interfering with itself, but it acts like a particle when it's interacting with matter.
Mm.
Like it changes its costume depending on the situation.
That's a fantastic analogy. And this whole wave-particle duality thing, well, it's a core principle of quantum mechanics, which governs the behavior of stuff at the atomic and subatomic level.
Okay, that is definitely a mind bender.
Oh,
It makes you wonder, what other crazy secrets is the universe hiding?
right. But here's the really wild part. This wave-particle duality isn't just limited to light.
It's not.
Nope. All matter, even the electrons and protons we were talking about, and even entire atoms, can exhibit both wave-like and particle-like behavior.
So the very building blocks of the universe can be both waves and particles. It's like the universe is playing some cosmic game of hide and seek, constantly shifting between different forms.
I know, it's wild. The more we learn about the nature of reality, the more we realize how much we still don't know. But hey, that's what makes it so exciting.
You're right about that. Okay, so we've explored this incredible spectrum. We've talked about how these waves interact with matter, and we've even touched on this crazy concept of wave-particle duality. But before we wrap things up, there was one more thing you mentioned earlier that I wanted to go back to. You said that the size of something is often related to the kind of electromagnetic waves it emits.
Oh yeah, that's a fascinating connection. It shows just how deeply electromagnetism is interwoven with the structure of the universe itself. For example, think about gamma rays. With their incredibly tiny wavelengths, they're usually produced in the most extreme and energetic environments, like nuclear reactions or the hearts of collapsing stars.
So these powerful, super tiny events produce the shortest wavelengths. That makes sense. What about other parts of the spectrum?
We'll take X-rays, for example. They're often emitted when the inner electrons of heavier atoms shift between energy levels.
So the size of an atom, or at least the part of the atom involved in emitting the X-ray, is related to the wavelength of that X-ray. That's really cool. What about as we move down the spectrum?
As we go down towards, say, visible light, we see it emitted when electrons in atoms jump between energy levels that are further apart.
Ah, so those electron transitions are happening on a slightly larger scale than the inner shell transitions that produce X-rays. That's why the wavelengths are longer. What about radio waves? Those have super long wavelengths, right? What's generating those?
Radio waves are typically produced by the movement of electrons in things like antennas and circuits, which are obviously much larger than atoms.
Ah, so the size of the antenna or circuit is connected to the wavelength of the radio waves it emits. It's like the universe has this built-in relationship between the scale of things and the types of waves they produce.
Exactly. It's like a cosmic fingerprint.
Yeah.
And it's something we can use to learn about the universe.
Okay, so we know this link exists, but why should we care? What makes it so important?
Because it acts like a cosmic ruler. It helps us understand things that are way too small or way too far away to see directly.
Ah, I get it. So by studying the electromagnetic radiation coming from a source, we could figure out its size and what it's made of, even if it's like millions of light years
Yeah,
away.
you got it. It's like having a superpower. For example, astronomers can use radio telescopes to study the radio waves coming from distant galaxies and map out the distribution of matter. And of course, doctors can use X-rays to see inside your body without having to do surgery.
So we're using the right wavelengths to investigate things at different scales. It's
Yeah.
like having a whole set of cosmic tools.
Exactly. And the more we learn about this relationship between wavelength and scale, the better we get at using these tools to explore the universe, from the tiniest particles to the largest structures in the cosmos.
It's incredible to think that these invisible forces are helping us unravel the mysteries of the universe. So we've covered a ton of ground in this deep dive.
We have. We've gone from the basic principles of electromagnetic waves to the mind-blowing implications of wave-particle duality.
And we've seen how these waves are not only fundamental to our understanding of the universe, but also to so many technologies that we rely on every day.
It's a story of scientific discovery, technological innovation, and the endless pursuit of knowledge.
It really makes you appreciate the power and beauty of the natural world. So the next time you turn on your phone, look up at the stars, or just feel the warmth of the sun, remember those invisible waves that are constantly at play, connecting us to the vastness of the cosmos. And listener, if this deep dive has sparked your curiosity, don't stop here. There's a whole universe of knowledge out there waiting to be discovered. Until next time, keep those minds curious. You know, we've talked a lot about different kinds of electromagnetic waves, like radio waves and X-rays and all that, but they all travel at the speed of light, right? So what really makes them so different from each other?
That's a great question. You're right, they all travel at the same speed in a vacuum, but the thing that really sets them apart is their energy.
Energy, huh? So like some waves are more powerful than others?
Exactly. And the energy of an electromagnetic wave is directly tied to its frequency. Higher frequency means higher energy.
Okay, that makes sense when I think about how X-rays can pass right through things.
hmm
They've got enough energy to do that. But what about the lower frequency waves, like radio waves?
Those lower frequency waves carry less energy. That's why we can use them for things like communication without, causing any harm. They can travel long distances and even pass through walls.
Okay, so it's all about how much energy each wave carries.
Yeah.
But what does that energy actually do? Like when a wave hits something, how does that energy manifest itself?
Well, remember how we talked about the electric and magnetic fields of a wave causing charged particles to move around?
Yeah, like those electrons and protons doing a little dance.
Exactly. The energy of the wave determines how intense that dance party gets.
So with a low energy wave, it's more like a slow waltz.
Yeah. But with a high energy wave, it's a full-on mosh pit.
Uh-huh. I like that analogy. So infrared radiation makes molecules do a slow dance and heat up, but X-rays have enough energy to blast those atoms apart.
You got it. And depending on the type of wave and what it hits, the energy can be absorbed, reflected, transmitted, even cause chemical reactions.
So we've got this whole spectrum of waves, each with its own energy level and its own unique way of interacting with the world. It's pretty amazing.
Yeah.
But is there a limit to how high or low the energy of these waves can go?
That's a great question. Theoretically, there's no upper limit to the energy a photon can carry. We've observed incredibly high energy gamma rays coming from distant cosmic events.
So there could be gamma rays out there with even more energy than we've ever detected. Whoa.
It's definitely possible. But as we get to those super high energies, it gets even weirder. The lines between waves and particles start to blur even more.
So it's like we're reaching the edge of what we understand about physics.
Yeah, kind of. It's a realm where quantum mechanics really takes over, and our classical understanding of physics doesn't quite cut it anymore.
It's a good reminder that there's still so much we don't know about the universe.
Absolutely, and that's what makes it so exciting. Who knows what incredible discoveries are waiting for us out there?
You're right about that. Well, I think we've covered a lot of ground in this deep dive. We've gone from the basic principles of electromagnetic waves to some pretty mind-bending concepts.
We have. We've learned about their origins, their properties, their interactions.
And we've seen how they play a crucial role in our understanding of the universe, not to mention in all sorts of technologies we use every single day.
It's been quite a journey.
It really has. So listener, the next time you turn on a light, use your cell phone or gaze up at the stars. Take a moment to appreciate those invisible waves that are constantly at work, connecting us to the vastness of the cosmos. And if this deep dive has sparked your curiosity, don't let it end here. Keep exploring, keep asking questions. Who knows what incredible things you might discover. Until next time, keep those minds curious.